Hi everyone, and welcome to this week's module on the energy from combustion. Energy actually is one of the most important topics for our society. Everything runs on energy. We're talking about getting food in the grocery store requires to grow the food. You need energy to bring the food home, to transport the food, requires energy to clean your water, transport your water from Northern California, requires energy. Almost every factor of our society requires energy. And this is globally. And that is why energy is often referred to, or oil specifically, is often referred to as the drug on our market. And even when President Bush was our president, he mentioned that us as Americans are addicted to oil. So it's a drug and we're addicted to it. So I want you to kind of think about these topics as we move forward into this lecture. Right now I'm going to give you an overview of the topic. This is a really fascinating topic. I hope you enjoy. If you look at the historic and projected energy consumption worldwide, you will find that for the most part, we are increasing our energy consumption globally. If you're looking at even the mature market economies, which is this blue line here, from 1970 to 2025 predictions, our energy will continue to increase, our consumption. Same thing with emerging economies like India, and even the transitional economies are still increasing. If you look at Human Development Index and energy consumption, they are highly related. So for example, human development's down here on this graph here from 0.3 to 1. And just a lower value means a lower quality of life, lower living standards, higher infant mortality, lower life expectancy. That would be a low quality of life. So if you look here, the energy consumption for low quality of life is not high in comparison to everything else. And this is just because people at this level here might not have access to electricity. Their needs are less. They don't buy as much clothes or products that require energy. India's also under this area as well. China is considered in this area an average quality of life, and they are actually higher in terms of energy consumption than your low quality of life regions. In very high quality of life, we are the biggest consumers. United States is considered a high quality of life region. We are the biggest consumers of energy. If you look at our energy consumption from the United States, you can see that majority of our energy consumption is from fossil fuels. 37% from petroleum, 29% from natural gas, 15% from coal. About 9% is from nuclear power, and only from this date of the slide, only 10% is from renewable energy. And renewable would be geothermal, solar, wind, biomass, and hydroelectric power. Again, realize that fossil fuel combustion is our #1 source of energy. Now, electricity is something more tangible for us, right? You plug in your computer, you plug in your phone, you turn on the light. We use electricity all the time, every day, even just to refrigerate our food. So electricity, if you look at how we generate our electricity, the majority of how we generate our electricity is from fossil fuel combustion. 39% coal, 27% natural gas. Okay, a little bit from renewables, and 20% from nuclear. One thing to note though, since 2007, from 2007 to 2013, our amount of coal, coal has actually dropped from 48% to 39%, though natural gas has increased from 22 to 27. So let's just do a quick review of what combustion is. Combustion is basically burning something. Here's an example of methane, which is one of the main components of natural gas. It's just CH4. You burn anything in oxygen. After you burn it, you get carbon dioxide gas and water gas. Notice water is a gas here. You know, when you're burning wood when you're camping, it is not raining down water, right? So you're producing gas. And importantly, you are producing energy. That's the focus of these lectures. So we're producing energy. If you look at this energy diagram here, okay, energy of reactants is on top. So that would be your methane and your oxygen. And your energy products are down below. That would be carbon dioxide and water. You have an energy difference here. Higher energy from your reactants, you have a higher energy, that's why it's on top, the higher energy of reactants and the lower energy of products. So that means these products have less energy, so you released energy. You released energy, so your products have less energy. And the energy difference of the heat released, heat is a form of energy, is negative 802.3 kilojoules. And it's just negative here because we're saying release. The negative value is not very important. It's just indicating that the energy is being released. Since energy is being released, we refer to this as an exothermic reaction. Okay, and that's why it's given it also negative value. That also indicates an exothermic reaction. But you know this, combustion. You burn something and it gets hot, right? When you're camping, you burn the wood so you stay warm in the night or early in the morning when it's freezing in the woods. You burn the wood to stay warm. You're releasing energy, releasing heat. One thing I want you to understand is this energy we are getting from combustion is occurring at the molecular level. So here is a molecule, for example. There's an energy holding the atoms together. So there's 3 atoms here. There's energy holding those atoms together. Remember, that's your potential energy. There's a potential energy there stored in those atoms, or those bonds actually, stored in those bonds. To break the bond though, you need to put some energy into it. Think about it. If you have blocks stacked together and you want to pull the blocks apart, you need to put some energy into pulling those blocks apart. Same thing here, you need to put some energy into pulling the blocks apart. So to note, breaking bonds always require energy. This is referred to as activation energy. We have a whole nother lecture about that, so don't worry. But breaking bonds requires activation energy, just like pulling apart the blocks. And just to note, forming bonds is the opposite. It releases energy. But if we're going to break the bonds from the reaction, when you burn fossil fuels, more energy is actually released than was required to break the bonds in the first place. So you release that potential energy that was stored in the bonds. So the energy is released in combustion. So overall, you used a little bit of energy, but you gained more energy ultimately. Now the question here is, so we can burn stuff and get energy. Does it matter what we burn? Can we get more energy from different things? And the answer is yes. It depends on what you burn, and you can get more energy from different things. So for example, if you look at methane, again, that's from natural gas. Okay, you have this energy. This isn't just a different unit in case you're going to get upset here. This is in kilojoules per gram, so that's why it's a different value. It's just a unit value. It's the same amount, it's just a different unit. So if you compare methane to, say, for example, coal, coal releases less energy when it's burned. And the same thing with ethanol. Ethanol, which you talk about getting energy from corn, for example, releases less energy. And glucose, even if you were to burn sugar, releases even less. So among these ones shown here on the slide, methane is the best one to burn in order to get the most energy. So I'm going to go briefly over the different types of fossil fuels. The first one is natural gas. You might see that if you have a gas-powered stove at home. And natural gas, as just like the name sounds, is in gas form. This is a table of the composition of natural gas. The number one thing in natural gas is methane, which is CH4. About 70 to 90% of natural gas is methane. You can also have ethane, propane, butane, that's about 0 to 20%. And then you have some other molecules, including hydrogen sulfide and some rare gases, but not much of them. To note, sulfide is one of the big bad air pollutants, right? But notice it's only 0 to 5%, so relatively it's not too bad in comparison to, say, coal. Petroleum is a liquid and a little bit of gas, but mostly liquid, right? It's called the black gold. Okay, this looks black. Crude oil is a mixture of many different compounds. A lot of hydrocarbons, which are just hydrogen and carbon, like the name sounds. So these are just some examples of some of the structures. And you also have some non-hydrocarbons, including your sulfurs, which again are pretty nasty impurities found in the crude oil. And you get some metallics as well, such as even some heavy metals, which are not good, they're toxic. Gasoline is actually a form of purified crude oil. So you take the crude oil and you purify it, and it's in a range of hydrocarbons. I'm just putting C's here, but remember there's hydrogens on these compounds. But it's a hydrocarbon with carbons between 4 carbons to 12 carbons. The last fossil fuel that we're going to talk about is coal, and this is the dirtiest of all fossil fuels. It's a solid, and it's a complex mixture of substances. It's not a mineral, okay? And you can approximate coal based on the following chemical formula. All right, so it has carbon, hydrogen, oxygen, nitrogen, and sulfur. Coal typically has the highest percent of sulfur compared to all other fossil fuels, and this is why it's referred to as the dirtiest of fossil fuels. Sulfur reacts with the water in the air and creates sulfuric acid and sulfurous acid, and that's famous for, again, the acid rain. All right, well, that's the end of our introduction to this module. I hope you enjoy learning about energy and fossil fuels. I'll see you guys next time.